Okay, so let's go ahead and take a look at number 6 then. So number 6 on that page 4 says x squared plus 10x plus 12. Okay, so we know that we want to find two numbers that multiply to 12 and add to 10. They need to have the same sign and they need to have both positives. So again, we've done this before. We'll look at all the factors of 12. So 1 and 12, 2 and 6, 3 and 4. And we need to find a pair that's going to add up to 10. So if you look through these, 1 and 12 would add up to 13, 2 and 6 would add up to 8, 3 and 4 would add up to 7. So what we see here is that there is no pair of numbers that multiplies to 12 and adds to 10. And sometimes that happens, and we call this prime. This is a prime trinomial. Okay, just like a prime number, the only way to get it is 1 times itself. Same idea here. It won't break down into binomials like we've been looking at. We can also, if it's easier for you to remember, you can also just say that it's not factorable. Okay. Now this is what I kind of worry about when we introduce this, because this does not mean as soon as you get stuck trying to factor a problem, you automatically say it's not factorable. Okay? You have to really have a reason, not just, oh, I can't think of two things, but here are all the possibilities for multiplying 12. I've looked at them all and none of them work. Versus just, I've kind of looked at it and I don't think I can find an answer, so I'm going to say it's not factorable. Okay, so just make sure that you're really careful about that. All right, then I want to look at number 7. Okay, so number 7, when you look at it, it does not look like one of these easier trinomials. It does not have a 1 in front of the x squared. We have 3x squared plus 18x plus 24. Okay, well, the hint that's there reminds you to always look for a GCF first. And as I said, we're always going to do that first. I kind of skipped that step, the other ones on this page, because we didn't need to look for a GCF, and I don't want to confuse you too much, right? If we have something, though, like x squared minus 3x plus 2, you can see pretty easily that there is no greatest common factor other than 1, because the only number here is 1, and there's no x here. So I can't take anything out of everything other than just a 1. But here we look at this, and we do have a greatest common factor that I can pull out. If I look at this, 3 goes into all of these numbers. I can't pull out an x because there's no x here, but I can pull out a 3. And we do that GCF method where we have, in parentheses, one term, for each term here. So I'm just going to do the GCF part first. Okay, and hopefully you can see where all these came from. 3x squared, if I take out the 3, I just have x squared. 18 divided by 3 is 6. 24 divided by 3 is 8. So that's where that came from. Now, I've pulled out the GCF. Now I look at what I have left. And again, when we did the GCF problems before, what we had left couldn't go any further, right? We didn't really look at that, but you didn't have any other methods to factor then. Now I know, what I have here is a trinomial. It's an easier trinomial. So I need two numbers that will multiply to 8 and add up to 6. This tells us the signs are the same. This tells us the signs are positive. So I still have to bring that 3 along, but now I can go ahead and write my two binomials. So maybe this is one you can do in your head, and maybe you have to write it out, and that's fine. But if we think about factors of 8, 1 and 8, 2 and 4, that also add up to 6, it's going to be 2 and 4, both positive. Again, you could have plus 4 and plus 2. If I want to check this, I have a couple of options. I'm going to multiply them 2 at a time. It doesn't matter what 2. So I can multiply these 2, get back to here, distribute my 3. Or you could also distribute your 3 first to get 3x plus 6 and then multiply that by x plus 4 and get back to this. 8 is similar, okay? 8 has a GCF to pull out first. Be careful of what you can pull out with 8. You can pull out a little more than we did here. All right, so that is another method of factoring. We just did factoring easier trinomials. Okay, and again, we call them easier because they have a 1 in front of the x squared. So something like this, if we couldn't take the GCF out here, this would be more of a harder one, right? We'll do those in a minute. We actually jump to a couple other things first, and then we'll go to factoring the harder trinomials. Okay, so the next thing we're going to do, the next kind of problem we're going to do, is factoring the difference of perfect squares. Okay, so let's again start by reviewing a little bit of multiplication. So let's say we have x plus 3 times x minus 3. And I multiply this, so x times x is going to give me x squared. X times negative 3 is negative 3x. 3 times x is plus 3x. 3 times negative 3 is negative 9. What happens here is I go to combine my middle terms, my like terms, and since the coefficients, the numbers in front, are opposites, 3 and negative 3, negative 3 plus 3 adds up to 0, so those cancel out. And I'm left with x squared minus 9. Okay. So it looks like I'm going to end up with one of my trinomials, but instead I end up with a binomial. But this binomial is in a special form. Okay? It's what we call the difference of perfect squares. Difference means there's subtraction. So there are two terms being subtracted, and each of these is a perfect square. Why is it a perfect square? Well, if I look at what I started out with, these two binomials are exactly the same other than that sign. So I had x times itself, x, and 3 times itself, right? One's positive, one's negative, but if I'm looking just at the number, it's the same number. So I end up with the difference of two perfect squares. So what I want to be able to do is, we'll talk about this at the end of this chapter also, but I want to be able to look at a problem and know what I'm doing with it based on what it looks like. So if I have two terms that are being subtracted and both are perfect squares, that needs to kind of set off an alarm bell in your head. So let's look at the next one. It's labeled number 9, and we have x squared minus 100. So if I'm going to factor this, I'm asked to factor, and I think, okay, the first thing I'm going to do is look for a GCF. And when I look here, there's a 1 here. So the only number they have in common is 1, and there's no x in this term. So I can't pull anything out as a GCF. But I look and there are two terms. They're being subtracted, and each one is a perfect square. So what I'm going to do is I think, okay, difference of perfect squares. I know that factors into two binomials. And the part in each binomial is the square root of these terms. So the square root of this goes here and here. Okay? First term, I take the square root of it, and that's what goes here and here. Square root of x squared is x, right? X times x equals x squared. Square root of 100. Square root of 100 is going to go here and here. So the square root of 100 is 10. Remember, we can think about the square root as a question, saying what number multiplied by itself equals this given number, plus and minus, one of each. Okay. I always have to have different signs. Different signs is what gives me a negative 100 here, the minus, and different signs is what makes the middle terms cancel out. So just to write it a little neater, my answer here is going to be x plus 10 times x minus 10. Again, you could have those factors written in the opposite order. Okay, next one, number 10. So we have 9x squared minus 49. Okay, so again, I look for a GCF first. 9 has some factors, right? 1 and 9, 3 and 3. If I look at 49 and I can try them on my calculator, none of those goes into 49 other than 1. So the only thing I can pull out is a number is 1. I can't pull out x's because there are no x's over here. So no GCF other than 1. 1 doesn't help me, right? If I divide out 1, I get the same thing. So we don't do anything with that. All right. So I do notice, though, it's two terms being subtracted, so it's a difference, and they're both perfect squares. 9 is a perfect square. X squared is a perfect square because the exponent is even. Remember, if that can be divided by 2, it's a perfect square. This is also a perfect square. So I'm going to turn this into my factors, my two binomials. So again, I take the square root of this first term and it goes here and here. The square root of the entire thing. So one really common mistake is people try to put 3 plus x and 3 minus x. Well, there is a 3 and there is an x, but they're together. So the square root of this whole thing goes here and here. So 9x squared, square root is 3x, it goes here, and 3x together goes there. And then square root of 49 is going to go here and here, plus and a minus. Again, with these, same as before, you check them by multiplying. So I could say 3x times 3x, that's going to give me 9x squared. This would give me positive 21x, negative 21x, those would cancel out. 7 times negative 7 is negative 49. Let's look at number 11. So 11 says 6x squared minus 384. Okay, now, right now this does not look like a difference of perfect squares. It's a difference, but 6 is not a perfect square, and if you take the square root of 384, that's not a perfect square either. But this is again where we need to remember to always look for a GCF first. So if I think about 6, I know that factors of 6 are 1 and 6, 2 and 3. Now I could write out all the factors of 384, which is probably going to have quite a few because it's big. Not always, but it could have more. But if I'm looking for a greatest common factor, really I just need to know if any of these also are factors of 384. Let's start with the biggest one, because then if I know that 2 is, let's say, which it is because they're both even, I still don't know if something bigger is. So start with your biggest one. If I take 384 and divide it by 6 on my calculator, I will find that it goes in evenly, okay? So 6 is a GCF of these two. I don't have to know that by looking at it, but I can find it out using my calculator. So x squared, oops, not minus 9. When I take 384 and divide it by 6, I'm going to get 64. Hopefully now you see this is difference of perfect squares. It is going to be x and x, 8 and 8, plus and minus. Okay, so next video, we're going to come back in a minute. We will do 12 and 13 and then move on to the next kind of factoring.